Good morning, children. Today's class, we will be discussing about the second property of positive integers, the fundamental theorem of arithmetic. Let's have a quick review of what are prime numbers and composite numbers. Prime numbers are those numbers which have factors as 1 and itself. Composite numbers are those numbers which have more than 2 factors. 1 is neither prime nor composite. These are the prime numbers below 50, which will be useful to you in the further exercises, as we do not have a specific method of checking whether a number is a prime or not. The only concept is prime numbers are having factors as 1 and itself. So, the prime numbers below 50, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43 and 47. Let me explain what is the meaning of fundamental theorem of arithmetic. The statement says every composite number can be expressed as the product of prime factors, the factorization being unique apart from the order in which the prime factors occur. Let me explain this statement with an example. Take the composite number 36. 36 can be factorized as the prime number 2, 18 with the prime number 2 again, 9, 3, 3 and 1. 36 is the product of 2 into 2 into 3 into 3, or it is 2 square into 3 square. Let's have the prime factors of 36 in a different way, starting with the prime number 3. It is 12, again with prime number 3, 4, with 2, 2, 1. You can see the prime factors of 36 as 3 square into 2 square. Here we can have one more method or two or more methods, but in all these examples you can see 36 is a composite number. It has unique factors of 2 and 3 occurring twice. The only difference is that we are taking the prime factors in a different order. Even then, the product of the prime factors according to the unique number 36 is not changing. Once again, I'll repeat. The fundamental theorem of arithmetic states that every composite number can be expressed as the product of prime factors, factorization being unique apart from the order in which the prime factors occur. Let's take the examples or the questions from exercise 1.2, question number 1. Express each number as the product of prime factors. The first subdivision, number 1, 140. 140 by 2 is 70, by 2 35, by 5 7, 7 and 1. 140 can be expressed as 2 square into 5 into 7. The same way, the numbers can be expressed as a factor tree. Let me explain that with the second example of 156. 156, we are going to express the prime factors in a factor tree. The number 156 is first factorized as 2 and 78. 2 is already a prime number. We are factorizing 78 as again 2 and 39. 2 is again a prime factor. You are factorizing it as 3 and 13. You can see here the last branches of the tree, both are prime factors, and so you are going to stop the factorization. The prime factors of 156 is 2 square into 3 into 13. A factor tree with blanks of the prime factors can be asked for the examination. Thank you. The application of the fundamental theorem of arithmetic is in finding the HCF, highest common factor, and LCM, the least common multiple, by using prime factorization method. Let me take 2 or 3 examples and teach you this topic. This topic has already been covered in smaller classes. There you are listing the factors, but here the factors will be expressed as powers. The only difference, you will be listing the factors as powers and deriving the rule for finding the HCF and LCM of 2 or more numbers. Take the example of 24 and 36. You are finding the HCF and LCM of 24 and 36. The step 1, 24 and 36 will be expressed as the product of prime factors. 24 can be expressed as 2 cubed into 3. 36 you are going to factorize as 18 by 2, 9 by 3, 3, 1. 36 is expressed as 2 square into 3 square. In the step 1, you will be factorizing the composite numbers given to you as the product of prime factors. A few students will be able to write it directly, but as a general method, I can give you a tip. Step number 2, you can see the prime factors which are occurring in both the numbers. You can see prime factors 2 and 3 are occurring in the factorization of the composite numbers. Here, both the factors 2 and 3 are common for both of the numbers. It may be or may not be there in further examples. The general method is, you are going to select the factors as highest common factor and the least common multiple. The word common gives you a clue to find out what are the common factors in these examples. In both the numbers, the common factors are 2 and 3. Now, what will be the power of those factors which will be considered for HCF and LCM? The HCF is the product of the least power of the common factors. The product of the least power of the common factors. You can see here the common factor, the prime factor 2. In the first number it is 2 cubed and the second number it is 2 square. For HCF, the least power of the common factor. For the prime factor 3, it is 3 to the power of 1 and 3 to the power of 2. The least power is 3. Therefore, the HCF is 4 into 3, which is the same as 12. By seeing the HCF, you can give or you can understand that the HCF value is smaller than both the given composite numbers. Coming to LCM, it is least common multiple. It is a multiple. Again, what are the common factors here? The common factors are 2 square and 2 cube. For LCM, the highest common factor or the highest power of the common factor we are going to take. Which is the highest power is 2 cubed, and for 3 and 3 square the highest power is 3 square. So the LCM will be 8 into 9, it is 72. You can see that the word multiple is telling you that the LCM answer will be definitely bigger than both the numbers of the composite numbers which are taken for workout. And there is a rule or a property for the HCF, LCM and the two numbers given. The property is the product of two numbers is equal to the product of their HCF and LCM. Here the two numbers we considered are 24 and 36. Let's find out the product of 24 and 36. 6 4s are 24, 4 3s are 12, 864. Thus the product of the number 24 into 36 is 864. Let's find the product of the HCF and LCM. 72, 864. Thus, when two numbers are given, the property states that the product of two numbers is equal to the product of their HCF and LCM. This property is not satisfied for three numbers. This property is applicable only for two numbers. Thank you. Let me take a second example of 48 and 150. The prime factors of 48 as 48 is equal to 2 to the power of 4 into 3. The prime factors of 150 as 150 as 2 into 3 into 5 square. In the previous example we considered the factors were only 2 and 3 and both were common. Here, if you can find 48's prime factors, it is 2 to the power of 4 into 3. 150, the prime factors are 2 into 3 into 5 square. As I explained to you, for taking the factors in a comfortable way, the second step is what are the prime factors which are occurring in both the numbers. You can see prime factor 2, 3 and 5. Now, here the 2 is common, 3 is common, 5 is not common. How can you make the power or the prime factor 5 as common is by writing 48 as 2 to the power of 4 into 3 into 5 to the power of 0 with the property of the law of exponents. Any number to the power of 0 is 1. That is, a to the power of 0 is 1. You are just expressing that 5 to the power of 0 here to make 5 also as a common factor for the number 48. 150 can be written as 2 into 3 into 5 square, which is giving you the idea that all the factors 2, 3 and 5 has come in both the numbers. Now, as per the rule, how the factors are taken for HCF and LCM. Take the first factor 2. 2 to the power of 1, 2 to the power of 4. The least power will be taken for HCF and the highest power will be taken for LCM. For the prime factor 3, it is 3 to the power of 1, it is 3 to the power of 1. That means both the numbers are having only one prime factor 3 or 1 3, or you are going to accept it for HCF as well as LCM. Take the prime factor 5. 5 to the power of 0 and 5 to the power of 2. Which is the minimum here? The minimum is 5 to the power of 0, which will be taken for HCF, and 5 square will be taken for LCM. Now, the value of 5 to the power of 0 is 1. The HCF value is 6. And the LCM will be the product of 2 raised to 4, 16 into 3, 48, 48 into 25, 40, 24, 16, 9. The LCM is 1200. And now, once again, what is the rule for finding HCF and LCM? HCF is the product of the least power of the common factors, and LCM is the product of the highest power of common factors. So, to make the factors common, you can take the help of the law of exponents, as the last law, a to the power of 0 is equal to 1. The next example from the textbook, find the LCM and HCF of the following pairs of integers and verify that LCM into HCF is equal to the product of two numbers. The first example is 26 and 91. The prime factors of 26 can be written as 2 into 13. 13 is a prime number. 26 can be expressed as 2 into 13. The prime factors of 91. 91 can be divisible with 7. 7 ones are 7 and 21 is 13, or again the prime factorization of 91 is 7 into 13. Now, as I mentioned earlier, a few students will be able to write it directly. For those who cannot, step 2 is, what are the factors? The factors you can see are 2, 7 and 13. The missing factors can be brought into light by giving the rule of a to the power of 0 equal to 1. The prime factor 7 can be brought in as 7 to the power of 0. The prime factor 2 can be written as 2 to the power of 0. For HCF and LCM, for HCF, least power of the common numbers, you can see here 2 to the power of 1 and 2 to the power of 0. 2 to the power of 0 will be taken for HCF, 2 to the power of 1, or simply 2 for LCM. For the factor 7, 7 to the power of 0 and 7 to the power of 1, 7 to the power of 0, 7 to the power of 1. 13 is common, which means it will be as a common factor for both of them. Since 2 to the power of 0, 7 to the power of 0, the answer is 1. HCF is 13 and the LCM is 2 into 7, 14 into 13, 4 3s are 12, 4, 4, 1, 182 is 182. The next part of the question asks you to verify the product of two numbers equal to product of their HCF into LCM. What are the two numbers under your consideration? That is 26 and 91. 91 into 26. The product is 2366. What is the product of the HCF and LCM? 182 into 13. Answer is 2366, which shows that the product of two numbers is equal to product of their HCF and LCM is verified. Number 2 and number 3, you can proceed with the same procedure. Question number 3, find the LCM of 12, 15 and 21. Considering three numbers, the LCM and HCF of 12, 15 and 21. The prime factors are by 2, the prime factors of 12, 2 square into 3, the prime factors of 15, 3 into 5, the prime factors of 21 as 3 into 7. Again, the method which I have been explaining, the children who can write directly can adopt that, or the others. What are the factors? You can see in all the three numbers are 2, 3, 5 and 7. The factors which are not currently present in that can be made written as 5 to the power of 0, 7 to the power of 0, 2 to the power of 0, 7 to the power of 0, 2 to the power of 0, 5 to the power of 0. You are going to write the HCF and LCM by taking the common factors from all the three numbers. 2 square, 2 to the power of 0, 2 to the power of 0. HCF will have the power of 2 to the power of 0. The second factor of 3, 3, 3, 3. All the three numbers you have the factor 3 in common. The next factor 5 to the power of 0, 5 to the power of 1 and 5 to the power of 0. For HCF it is 5 to the power of 0 and for LCM it is 5. 7 to the power of 0, 7 to the power of 0 and 7, which gives you for HCF 7 to the power of 0. Since the value is 1, the HCF takes the value of 3 and LCM 1260 into 7, which is equal to 420. And then the property that the product of two numbers is the same as the product of their HCF and LCM is not satisfied in the case of three numbers. The next example is of find the HCF of 8, HCF and LCM of 8, 9 and 25. 8, 9 and 25. The prime factors of 8 is 2 cube. Prime factors of 9 is the same as 3 square. And the prime factors of 25 is the same as 5 square. Here you can see that 2 cube, 3 square, 5 square, all the three numbers, they do not have a common factor other than 1. So the HCF of all these three numbers, they do not have a common factor. The HCF is 1 and the LCM of these three numbers which do not have common factor is the product of these three numbers. The example is given here. This also is a note for you. Such numbers which do not have common factors are called coprime numbers. So the HCF of coprime numbers is always 1 and the LCM of the coprime numbers is the product of the numbers. Thank you. Exercise 1.2, question number 4. Given that HCF of 306 and 657 is equal to 9, find the LCM of 306 and 657. This can be asked as an important 2-mark question. Just apply the property. The product of two numbers is equal to the product of their HCF and LCM. The two numbers under consideration here are 306 and 657. 306 multiplied by 657 is equal to, the HCF is given as 9, LCM has to be found out. The quick method of finding is you will only simplify. So LCM is equal to 306 into 657 by 9. You can see that number 9 is divisible in both the numbers, but simplify only in one of them, as 9 3s are 27, 36, 34. So the LCM answer will be 657 into 34. The LCM is 22,338. It's a very common 2-mark question which is asked by the boards. Question number 5. Check whether 6 raised to n can be expressed as, can end with a digit 0 for any natural number n. Check whether the number 6 to the power of n can end with a digit 0 for any natural number n. The explanation for this question will be in such a way that it's easy for you to understand is, write or a few examples of numbers which are ending with 0. A few numbers I will write 30, 20, 100 and 40 or 70. The prime factors of 30 are 2 into 3 into 5. The prime factors of 20, 2 square into 5. The prime factor of 100, 2 square into 5 square. For 40, it is 2 cubed into 5. And the prime factor of 70, 2 into 5 into 7. What do you observe about the prime factors when the units digit is a 0 in all these numbers? You can see here the prime factors 2 and 5 are compulsory for the numbers ending with the digit 0. If you understand this explanation, the number 6 to the power of n can be written as 2 into 3 to the power of n, where we do not have the prime factor 5, which shows that the number 6 raised to n cannot end with a digit 0 for any value of n. How do you write the answer is any number ending with 0 will have 2 and 5 as prime factors, but 6 to the power of n is equal to 2 into 3 to the power of n do not have the prime factor 5. Therefore, 6 to the power of n cannot end with a digit 0 for any natural number n. Question number 6. Explain why 7 into 11 into 13 plus 13 is a composite number. Explain why 7 into 11 into 13 plus 13 is a composite number. These questions are asking you to justify that this is a composite number. You can see the prime factor 30 is common. 13 into 7 into 11 plus 1. 13 into 78. Even without prime factorization, we can say that this number is a product of more than 2 factors. It is definitely a composite number. Or since 13 into 78 into 1 have more than 2 factors, 7 into 11 into 13 plus 13 is a composite number. This completes exercise 1.2. The word problem, when you read, you will understand the clue is they will meet after a multiple of the next time, or which shows that you have to find the LCM of the time which is taken by the two people, Ravi and Sonia. Once you find the LCM of 12 and 18, you will get the next multiple of the time when they meet each other at the starting point. Thank you.